So what did we learn? Well, we learned a general lesson. And what we would like to do, we have the mean flow with a vortex. We would like to shift it into the direction of the potential flow. Unfortunately, we cannot do it. So what we are now doing, we have to play with the natural dynamics. We just use another fluctuation to change the base flow via changed Reynolds stresses. So we go somewhere close to the base flow. And since we cannot control the von Karman vortex structures directly, we support the enemy of our enemy. And this is a strategy. So often you cannot kill the structures which you want to kill. I can give you many examples of this, but it's always easy to excite a structure. And then you have to excite the right structures, so the enemy of your enemy. And what are the implications of control? Well, let's look at our two oscillator models. So we call it generalized mean field model again, and we put in some numbers. So it's always the small quantities are 0.1. First frequency is 1, and we have high frequency forcing, so we call it 10. And we just look at one growth rate. So this growth rate is positive, damped here. Now, what we would like to do, we would like to mitigate the fluctuation energy von Karman vortex shedding and penalize our actuation. And the first idea which comes to mind, okay, let's do linear control. Let's linearize. If you linearize, you get 1.01. So these terms are missing. So the second oscillator is stable. Your control does not need to do anything, and the first oscillator cannot be affected. And that means linear control, the first oscillator is uncontrollable in linear control. You can only control it if you understand a bit of the nonlinearity. And of course, you know what you need to do. You need to excite the second oscillator above a certain threshold, 0.1, to have a negative growth rate here. So this is your understanding, which you have to bring in order to make control approaches work. Good. So the general approach, just a recap. You have a steady solution, base flow deformation, a component from unsteady vortex shedding from your actuation. So these are the two frequencies. First frequency, second frequency, you always need two modes. Each of the contribution has one corresponding shift mode, Reynolds stress contribution. So you always end up with 6 modes. And you can show that the general structure of the dynamics derived from harmonic balances and so on looks something like that. So we have, I will not go into much detail. You can now do the control design. You only have to focus on the growth rate of the first oscillator, which we have seen already earlier. You can do energy-based control, so you can make the ansatz B. You want to destabilize the second oscillator, so that you can make this ansatz, and you can say the fluctuation level has to be on a certain level. So you can want to identify this function as F, and you can do so from energy-based control. Long story short, I have identified this in a thing for the D-shaped body, where we have another frequency, and we have applied a corresponding control scheme, and it has worked reasonably well. Now, for the dynamical system, what we have here, without forcing, this is the first oscillator, A1, A2, A5. So you have the limit cycle here. On the second oscillator, you are at 0. Now, the transient from the steady solution here to the limit cycle, you start your actuation, you spiral backwards, and here you spiral outwards on the limit cycle, and this oscillator kills that oscillator, and you can see it more directly if you look at the two shift modes. So A5 is the amplitude associated with the first oscillator, and A6 is the amplitude associated with the unstable oscillator. So what you are doing here, you start here, natural shedding, and then you ramp up the fluctuation energy in the first, and have a certain change in the shift mode. You go up here, then you stop actuation, and then you go somewhere here. So this is what you get from your dynamical system. Why are we talking this? There are many examples which fall in this category. So there's high frequency forcing, which Ari Glaser is frequently talking about. There's low frequency forcing and so on. They can all be described in this framework. So one was a D-shaped body, high lift configuration, and I could add many more examples here. So the mechanisms which we have learned now for stabilizing an instability may be encapsulated in this model here. We have one component from Karman vortex shedding, another component could be low or high frequency shedding, and we have a base flow variation. Some forcing may be able to directly communicate with the first oscillator, and then we have to do phasor control. So what we have seen in the first example or in the numerical example. In some strategy we cannot do this, then we have to excite the second oscillator. So we have to use some open loop frequency crosstalk to kill the first oscillator. So it's a destabilizing control using frequency crosstalk. And what I did not discuss, because it's so easy, what you can also do, you can blow the instability away. So you can take, for instance, the D-shaped body, you can make your core undersurfaces there, you simply blow, and you blow the wake away, and you prevent vortex shedding. So in terms of the model, this would correspond for changing the mean flow, and thereby the unstable dynamic becomes a stable dynamic. So these are several strategies of taming an instability. Now there are many more things. So if you look in the literature, you find constant forcing, periodic forcing, opposition control. So we have seen it for the turbulent boundary layer, phase and frequency crosstalk. So this is essentially implicit. You typically have single input, single output. This is the effective mechanism. But there are many opportunities for multiple input, multiple output control. For instance, it's often found that if you use multiple frequencies, it's better than using a single frequency. How are you going to optimize those? Then at some point you may be curious. Okay, you have you do not only want to have multi-frequency, but you also want to have some sensor signal. Maybe you also want to incorporate noise. So this is a general idea of a controller which you get from the literature. And the next thing is maybe you want an automatic identification of the frequency crosstalk mechanism, automatic actuator selection, automatic sensor selection. So this looks like a big fantasy which can never be realized in any practical terms, but it turns out the solution is amazingly simple. And this is what I will talk now. Other questions so far? There were not, let's say 6 modes, yes.
Okay. But you didn't identify them POD?
Well, you can take the first 2 modes are POD, the second 2 modes are POD, and the other, the shift modes need to be identified in a different method. These are empirical modes, yes, and they are effectively a POD mode if you look at the right transient, if you process them in the right way. Good question. So from your experience. So this is the starting point.
So maybe a bit in the same line. In other configurations, how much? I mean, you will also need to reuse your experience. This is okay, it's a way, but let's say you control a completely different problem. I don't know, a liquid film flow or something completely different. So you have to restart from your experience.
You have to restart from there, but normally you think you have another flow, and essentially your old experience becomes invalid. But if you find that if you excite one frequency, and you change another frequency. So if you have this frequency crosstalk mechanisms, and if you believe that the dynamics is linear quadratic, it needs to satisfy these equations. So this is, I would claim, a general property of linear quadratic dynamics, which have a self-amplified, amplitude-limited natural dynamic, which is killed by an excitation of a stable high frequency or low frequency dynamics. So it's a dynamical problem. It's not a physical problem.
Say linear quadratic. What's linear and what's the quadratic?
Well, you look at the Navier-Stokes equation. Can you answer me the question for the Navier-Stokes equation?
I'm talking more about the reduced order model that you built, right?
Well, you can derive the reduced order model.
That is
What?
linear and the base is quadratic.
You look at the Navier-Stokes equation. So which terms do you have? You have the viscous term. So the viscous term is, of course, linear. You have nu Laplace u. Now you look at the convection term. So if you take the base flow and the fluctuation u0 u prime, it's linear. It has to be in the linear term. Now you look at the other linear term, so u prime u0, so nabla u prime u0. It's also a linear term. So there's a linear part of the convection term, which also goes into the linear term. And then there is a residual part, so nabla u prime u prime. Essentially, if you average this would be the Reynolds stress. So this part goes into the quadratic term. And so if you look at the pressure equation, so then you have the pressure Poisson equation. It also has a linear and quadratic term. It turns out the quadratic term is something which you can almost always neglect. So the pressure term typically only changes the linear part. And you, as mentioned, you can derive everything what I've shown you now is Navier-Stokes consistent. So the slaving is your Reynolds equation. And the other equation is your equation for u prime. Thanks for letting me make this point. So we have now seen an example of model-based control, and maybe I've convinced you that under some conditions you can derive a model for your plant. Typically, if you have 1, 2, perhaps 3 frequencies, but would you be optimistic if I tell you you have broadband turbulence, if you have a turbulent jet? Would you try to build a model which you use for control under these cases? Well, if you do runs, then essentially you kill all the dynamics, and you cannot do control anymore. If you yes, but U-runs, what can you resolve with U-runs? You cannot resolve, say, different frequencies, shear layer growth, and so on. With U-runs, you typically only, the survivor of a U-runs is typically an oscillation. Typically, you get a periodic solution, and you don't get a U-run solution which shows you broadband spectrum. If you get that, then you're not doing U-runs anymore.
No, but I mean, you're using your runs to get your Reynolds stresses. I mean, what you are doing is you are exciting Reynolds stresses in your wake to kill the wake. That's what.
Yes, right. And there are 2 ways. So for instance, so one thing, you use a fluctuation as your agent, and the fluctuation changes the base flow via the Reynolds stress. And the next thing is if you do constant forcing, then you change the base flow directly. So this is the brute force killing of the instability, and you can change the base flow directly, or you can use the Reynolds stress as your agent. And at the end, you typically live on a manifold, the manifold which is determined by the Reynolds equation. So we have seen this model-based control, which may be associated with Norbert Wiener. And we have seen the movie of the eagle doing the amazing maneuver on the landing on a rock under gusty conditions. I have discussed already that we can, that this eagle does smart trial and error. Smart trial and error means you try a controller, you measure the performance, you try another controller, and so on. You hope to optimize things with some clever algorithm. So in case of the eagle, it means the death of many eagles and millions of lives of evolution. But you can do it in a way that no animals are harmed. And you use some other approach from the mathematics community. The cost function has typically two parts. So one part what you want to achieve, for instance, drag power reduction, and one part is your cost, which you have to take into account. So you typically want to minimize the cost. And what you typically want as an engineer, you want to minimize your cost regardless how. So you are not a priori interested in a model, you are interested in solving a regression problem, meaning finding a controller, let's say here a sensor feedback to the actuation, in such a way that it minimizes the cost. So this is a regression problem, but you see already it's a pretty tough regression problem. You have to see the effect of one function on the overall dynamics, and I would claim this is a variational problem. Control theory leads to a variational problem of the controller. And the question is, how can we solve it? So, of course, we don't want to take the Navier-Stokes equation or anything like that. So this is already difficult enough. Somehow we need a data-based approach. And now we assume something. Let's start simple. Suppose we have one feedback control. Let's take the cylinder oscillation where we rotate. So now our B here is the rotation speed of the cylinder. And we measure, for instance, the lift and the lift derivative. Now we would like to find the parameters P1 and P2. Seems a simple problem. I will introduce you now to an algorithm which we will use and generalize later, so the genetic algorithm. So who of you knows the genetic algorithm? Okay, I would say maybe 30%. And who of you has used them already? Almost the same amount of people. Wow, good. Anybody wants to explain it? No. So what you are doing here, now you discretize your parameter in a kind of funny way. You say, I discretize my parameter in terms of 3 bits. There's a value here corresponding to the bit 0, 0, 0, 0, 0, 1, and so on, and 1, 1, 1. So you discretize your parameter in 8 bits, and the other one also in 8 bits, so that if you put these 3 bits together in a 6-bit thing, this characterizes your controller. And you now do you want to optimize your controller with these bits, and there's a technique which also emulates nature. First, you start with some generation and you use random bits. So these are your random controllers, your random parameters, typically of the order of 100. The next thing what you do is you determine the cost. So you test them in your experiment or in your simulations, and then you resort them in such a way that the good controllers are at the top and the bad controllers are at the bottom. In this evolutionary algorithm community, this is called, the controllers are called individuals. And then you want to create a new generation which is supposedly better, which finds better minima or climbs down a found minimum. The first thing what you do, you take your winner of the first generation and put it in the second generation. We probably agree that this is a smart thing to do. And then we apply some genetic operation which may create some new controllers. One operation is called selection. That means, or replication. You take one of the controllers and put them in the next generation with some probability. Why might this be useful? Well, this is your memory preservation. So you don't want to start from scratch. And the other thing, your chances of taking the first individual the first individuals have a higher chance of being selected than the worst individuals. So to some extent, this is your memory of your control landscape. Another operation is mutation. So what you take the controller, you take a random number of bits and you replace the bits with random other bits. So we probably agree that when you do a mutation, you find something new. So maybe you find a new minimum. So the mutation essentially does exploration for you. And there's another operation which your parents did with you, crossover. So you have some genes of your father and some genes of your mother. And which genes are here now randomly chosen? So I say, okay, these genes and these genes are now replaced. And the crossover tends to breed better individuals. It's not obvious from a mathematical perspective, but it's frequently found. And now you have your new generation. In the new generation, you test them in the experiment or in your simulation. You determine the cost, and you start again until some convergence criterion is reached. And it looks like, well, brute force trial and error. So when I saw these approaches the first time, I got stomach aches. So it took me several years of waiting before I would apply them anywhere. But it turns out they can be very efficient, as we will see later. Maybe a visual, why didn't we could have done a gradient search. So now we had two parameters. Nobody can prevent us to look at a slightly different parameter and slide down the gradient. If this is here our control landscape, so the performance with P1, P2, then the chances are big of sliding into local minima. So what you want to avoid with an evolutionary algorithm is you start with an army and you want to make sure that you, on the one hand, slide down the minima which you have identified and maybe find new minima which you would have missed with a gradient approach. And we have, I've shown you the evolutionary algorithm, something like genetic algorithm, for this one already in my first lecture. Now, we would, at the end, we would like to identify a controller. What is a controller? In the simplest case, the controller maps our sensor signals, maybe 10 sensor signals, in 10 actuation commands. And regardless which approach we are using, at the end, we have a finite number of operations. So maybe the exponential and the four basic operations. This is one thing. In the real realization, we have a finite number of variables which we can use. So this is our registers here. And we will always do a finite number of operations, so which are listed here. The controller now is coded in following way. So in the first, let's say in the first 3 registers, you put your sensor reading. You say your force register shall be interpreted as your control input, and then you may have a couple of constants. So this is how you may use the registers. Now you do a couple of operations. For instance, this is a random matrix. First you take register 5 and register 1 and do the subtraction. So you replace the first register with R5 minus R1. Then you do something with something similar with in the second operation. And the fourth you use the divided operation, and so on and so on. So now you do 5 operations. And if you do these 5 operations, first step, second step, and then the last step. In the last step, you have replaced the control signal 0 with something like that here. So this is the controller. This is something which you need to understand. And of course, it works also if you have 2 actuation inputs, 3 actuation inputs, and so on. So this is something which do you feel comfortable with that? to some extent, it's very simple. If I tell you the controller is a finite number of operations, which translates your sensor signal into your actuation command. The peculiarity here is that things are discretized in terms of a matrix. So you have an integer matrix. Now, what is a bit funny here is you have a finite number of control laws now, but it will explode. So let's take this. So you have roughly, let's say, six possibilities for each element. Let's say 5. So in the first row, you have 5 times 5 times 5 times 5 possibilities, and you have 5 instructions. So you multiply it. You take it to the power 5? So you get very quickly astronomical numbers. So you don't want to go through all possible controllers. You must find a smarter way. And probably, since I've shown you already the genetic algorithm, you will probably see, oh, maybe we can stack these things in some way and apply a genetic algorithm, right? So instead of zeros and 1, we have a finite number of elements here, and maybe we can do similar operations with this matrix. And actually, this is what we are doing, and the technique is called linear genetic programming. So here use the first generation with some random matrices sorted by performance. So this is the window. This is what you directly copy in the second generation. Now you do some, you randomly select some other elements for replication. Let's say you take the second one. Then you may do crossover with numbers 3 and 4. So crossover means you replace some lines with some other lines. Shown here. And another operation is you randomly take some integer values and replace it by random other integer values. So these are the same operations which you now use for your controller. So in principle, you are doing pretty much the same thing like in the genetic algorithm. So probably you are confident now that in principle, you can program this on a weekend yourself. And so what we are doing here, same thing. We typically test of the order of 100 individuals. Before we had a probability which was larger for the first individuals than for the second. There's another way of realizing it, which is somewhat more convenient. It's called tournament. So what you take, you randomly select one of these individuals, you put them in the tournament, and then you take the best individual of the tournament. And so this way, the better individuals have a larger chance of being selected. And in the other case, you would have to assume a probability depending on the cost function, and this is a dangerous undertaking. So this tends to be more robust. But in principle, you do the same operations. You randomly choose the individuals, then you have your tournament. You randomly choose your operation, then you with random parameters and so on. This way, how you build the second generation. Sort the individual, test them, sort them, and do it again until convergence criterion is reached.